So this is the story of the curious case of Orville, the zebra jumping spider. And these calculations that I'm about to tell you about, and I won't go into them in any great detail, they came out of a very simple video. We had a jumping spider, Orville in this case here, but we did it for all of our jumping spiders. We put them in plastic containers that had a top to bottom length of about 12.2 centimeters, 122 millimeters, and we would whack the top, pretty hard sometimes, and then see if we could elicit the spider to jump to the bottom, because we wanted to see how much time it took, because these spiders really move quickly, and I was curious about the kinematics of jumping spiders. Okay, this is Orville. Go ahead. Got it. So I estimate that the spider can stretch its legs about 2 millimeters. So the whole spider's length is about maybe 4 or 5 millimeters. That's generous. And so its leg stretching 2 millimeters. So if that's the contact distance before it can no longer propel itself, then the distance that it falls is a little bit less than the 122 millimeters, about 120 millimeters. And using that, I was able to calculate the initial speed of the jumping spider, and it turned out to be an astounding number. 2.5 and change, basically 2.52 meters per second, which turns out to be about a little over 9 kilometers per hour, or 5.62 miles per hour, which is an astounding speed. Okay, now I want to get the acceleration, so I took the speed that I calculated the spider to have before it became disconnected from the top of the plastic container and could no longer itself propel itself. So based on that and an estimated contact time of about 0.002 or 2 milliseconds, about a half a frame, because if you were to look at the slow-mo video in greater detail, you'd see there's a spider in the next frame. The spider's already disconnected from the top of the frame. So I calculated an initial acceleration of 128.4 g, which is quite astounding. But these are not numbers that are unknown to the scientific community. Now, the other thing is, when you look at the regular video, it's a nothing burger. But when you look at the slow-mo video, which you ran the regular video, we ran it through something called CMV Free, which is an app for iPhones. And iPhones give us a frame-by-frame of about 4 milliseconds, 240 frames per 240 frames per second, 0.0044, I think, milliseconds per frame. So roughly about 4 milliseconds per frame. When you watch the spider hit the bottom, in the very next frame, it's already coming up, which I thought was amazing. Okay, but apparently if you were a spider freak or jumping spider aficionado, maybe that's a better way to put it, you wouldn't think so. In any event, I estimated the turnaround time for landing to already being back airborne of 1 frame, or about 4 milliseconds. So based on that and watching the spider go up and then come back down, I calculated the initial speed that the spider had ascending, and it was only about 0.4 meters per second, 0.396 meters per second, compared to the speed that it had when it was about to land. Did I calculate that? Yeah, I did. It was 2.948 meters per second. So it was moving pretty quick. Now, I said it was 2.52 meters per second when it left the top of the plastic, but then, of course, it acquires speed as it's falling under the influence of gravity. So if just before it hits the plastic, it's 2.94, when it comes back up, it's only 0.4, roughly, okay? So there was quite a diminishment in speed, and I wanted to calculate that in terms of kinetic energy. And it looks like the kinetic energy is 1/2 mv squared, 1/2 mv squared. I don't need to know the mass of the spider. I just need to take the ratio of the kinetic energies. And it looks like the ratio of the kinetic energies is about 50-1. Now these are the translational kinetic energies. So when the spider is about to hit the ground, or the bottom of the plastic container, it's all translational kinetic energy, linear kinetic energy. But when it goes back up, it does this Simone Biles thing. So I have to give Orville at least a bronze in spider jumping. And so it looks like about 98% or so of the original translational kinetic energy is gone. Where did it go? Well, it went into rotational kinetic energy, I think, plus probably some drag. But I'm guessing the spider must do some kind of a corkscrew-like thing upon landing. So whether, it has the more traditional mechanism of some kind of a lever of sorts, like the spring spider, these spiders don't have that. So I'm thinking they twist, and so they have potential energy, elastic potential energy in their twisting action, but then that's released as rotational kinetic energy. In any event, if you look at the frame-by-frame analysis, now I'm going to show you one video where you can see the time at the top, and it's a series of pictures from the slow-mo video, and I think they're clocking in at 1 second so that you can watch the actual movement in slow motion. So, and then the second video, which is a bit larger and easier to follow in terms of the motion of the spider. So you see the spider is rotating in the horizontal plane and apparently in the vertical plane too. And to my astonishment, when this spider goes up and then comes back down after that first bounce, it stays on the ground. So there's a little bit of a damping motion. So it goes up, does its Simone Biles, then it comes back down, and there's a little hiccup, but its feet do not leave the ground, the plastic at the bottom of the container. So that's pretty stunning, don't you think? Now there's other calculations I could possibly do as well, like change of momentum, the impulse force, the impulse and therefore the force, if I can estimate the time of contact. But I didn't do those. I just wanted to show you this video because literally all the videos what jumping spiders are going to be like this. So it's really just another indication of why I need a 1,000 frame per second camera, because I can't get the detail on these guys because they're moving so fast. It's stunning. Okay, but I thought you would enjoy this video, okay?